This paper investigates the convergence of the random batch method with replacement, RBM-r, for simulating interacting particle systems. RBM-r is an efficient algorithm that reduces the computational cost from O(n)² to O(p)n) per time step, where p represents the batch size. The algorithm randomly picks a small batch of size p, and only the particles in the picked batch interact among each other within the batch for a short time, with the weak interaction replaced by a strong interaction. The authors provide a rigorous proof of the convergence of RBM-r with an explicit convergence rate. They also obtain an improved rate when there is no diffusion in the system. The techniques used in the analysis can potentially be applied to study kinetic Monte Carlo (KMC) methods for other systems, including the stochastic Ising spin system. The interacting particle system is modeled by a first-order pairwise interacting particle system in Rho, described by a stochastic differential equation (SDE) system in Ito's sense. The system consists of n indistinguishable particles, each interacting with each other according to some interaction force. The interaction force is a weak interaction, usually of strength 1, n, which requires O(n)² complexity per time step. In contrast, RBM-r replaces the weak interaction force with a strong interaction force 1, p within pairs selected in a batch with size p. This replacement dramatically reduces the computational cost and provides an unbiased approximation for the force-velocity field of the original interacting particle system. The consistency property of RBM-r is crucial in the analysis, particularly in proving the convergence of the method. The authors also discuss the applicability of RBM to other systems, including non-binary interacting particle systems, systems with unequal weights, charges, or volatility, and systems with degenerate or multiplicative noise. They further mention that RBM can be extended to jumping processes like the stochastic Ising model. Overall, the paper provides a comprehensive analysis of the convergence of RBM-r for simulating interacting particle systems, with potential applications to various fields in natural and social sciences. The random batch method, RBM, is a novel algorithm for simulating interacting particle systems, which significantly reduces computational complexity to O(n)t)n. It was first proposed in 2020 and has since been applied to various practical algorithms, such as the random batch yield method for molecular dynamics, sampling, interacting quantum particle systems, second-order interacting particle systems, multi-species stochastic interacting particle systems, the Poisson-Nernst-Planck equation, and the homogeneous Landau equation. There are two approaches to RBM: RBM-1, random batch method without replacement, and RBM-r, random batch method with replacement. RBM-1 divides 1. n into n, p small batches of size p at each time tk, where particles interact within each batch. RBM-r, on the other hand, uses a pick-interact algorithm, where at each tk, a batch ck of size p is randomly picked, and particles in the batch interact among each other within the batch for a short time kappa. The interaction force in RBM-r has the consistency property as discussed in equation 1.2. Both RBM-1 and RBM-r share similar implementation details, convergence properties, and computational complexity. RBM-1 converges to the original interacting particle system as kappa right pointing arrow 0, with a convergence rate under Wasserstein 2 distance of O, square root kappa plus kappa squared. RBM-r also converges to the original interacting particle system at time t, with an explicit convergence rate. The geometric ergodicity of RBM dynamics and some convergence of numerical discretization for RBM of dynamics have been well studied via specific coupling methods. A sharp error bound for the numerical discretization of RBM has been established, motivated by advanced techniques in data science and machine learning communities. The mean field limit, the n-right pointing arrow infinity region, of the random batch method has also been studied in recent years. This paper bridges the gap in the convergence analysis of the RBM-r algorithm, a kinetic Monte Carlo method applied to interacting particle systems. The authors establish the convergence of RBM-r in Wasserstein 2 distance, under certain conditions on the potential function V and the interaction kernel K. The main result, stated in Theorem 2.1, bounds the Wasserstein-2 distance between the first marginal distributions of the interacting particle system and the RBM-r algorithm by c kappa caret 1/4, where c is a constant depending on the system parameters and kappa is the time step. The proof relies on a novel coupling method, introducing an intermediate dynamics IPS, with n copies of the interacting particle system after random time change. The authors utilize the diagonal principle during the analysis, coupling the Brownian motions in a specific way to facilitate the proof. The key insight is to synchronize the paired dynamics, x, using the same Brownian motion, allowing for the derivation of a bound on the Wasserstein-2 distance. The convergence rate O, kappa caret 1/4, is weaker than that of RBM1, due to the use of random time change in the coupling construction. However, an improved convergence rate O, kappa caret 1/2, can be obtained when there is no diffusion in the system. The authors discuss the technical challenges and limitations of the proof, including the use of H. Diaresis-Older's continuity property and the construction of the paired dynamics. The analysis is based on the exchangeability of the particle system, allowing for the use of a coupling method to prove the convergence result. The authors define an intermediate dynamics IPS, and utilize the diagonal principle to couple the Brownian motions in a specific way. The proof provides a rigorous analysis of the convergence of the RBM-r algorithm, shedding light on the behavior of the interacting particle system. The paper highlights the significance of establishing robust methods for the convergence of kinetic Monte Carlo algorithms, such as RBM-r, to dynamical systems. The results contribute to a deeper understanding of the behavior of complex systems and provide insights into the development of more efficient algorithms for simulating interacting particle systems. The authors propose a random batch method with replacement, RBM-r, for solving interacting particle systems, IPS. The IPS is defined as a system of n particles interacting through a potential function V and an interaction kernel K, with each particle subject to a Brownian motion. The RBM-r algorithm is a discretization of the IPS, where at each time step, a random batch of particles is chosen, and the interaction force is calculated based on this batch. The authors construct a coupling between the IPS and RBM-r, which is crucial for the subsequent analysis. They observe that each n-body system in the IPS is a random time change from the corresponding system in the RBM-r, induced by each index I. This random time change relation is used to estimate the distance between the IPS and RBM-r. The authors propose a two-step approach to estimate the distance between the IPS and RBM-r. The first step is to compare the IPS and its corresponding interacting particle system, IPS, which is a random time change of the IPS. The second step is to compare IPS and RBM-r. The authors use the Holder's continuity property, the law of large numbers, and the Lipschitz assumption for the interaction kernel K to establish the estimates. The main result of the paper is the convergence of RBM-r in Wasserstein-2 distance to the IPS, with an explicit convergence rate. The authors assume that the potential function V is strongly convex and has polynomial growth, and the interaction kernel K is bounded and Lipschitz. Under these assumptions, they prove that the Wasserstein-2 distance between the first marginal distributions of the IPS and RBM-r converges to 0 with an explicit rate, specifically O, kappa caret 1/4, where kappa is the time step. The authors also discuss the organization of the rest of the paper, which includes the proof of the main theorem, technical lemmas, and a conclusion with discussions on possible improvements and applications of the analysis tools to other algorithms. The paper discusses the convergence rate of the random batch method with replacement, RBM-r, to the interacting particle system, IPS, in a mean-field limit. It is shown that the RBM-r converges to IPS as the number of particles n and the batch size p tend to infinity, with a convergence rate of O, kappa caret 1/4. The convergence rate can be improved to O, kappa caret 1/2, when there is no diffusion, i.e., sigma equals 0. To prove the main result, the authors introduce an intermediate dynamics, IPS, which consists of n copies of IPS after a random time change. They define a triple of dynamics, x, 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 with the same initial state, and couple the Brownian motions in such a way that xi in RBM-r and xi, I in IPS, are synchronously coupled. This means that IPS defines n pairwise independent interacting particle systems, where for each fixed I, all particles xl, I, 1 is less than or equal to L is less than or equal to n, move forward or stay still simultaneously according to whether the event, I element of CK, happens at the kth interval. The authors also provide a high-level overview of their proof. They use a coupling method to estimate W2, ρ 1, npt, ρ 1, t, the Wasserstein 2 distance between the first marginal distributions at time t for RBM-r and IPS. The key idea is to first establish a bound on the distance between x and x, then a bound on the distance between x and x, and finally combine these two bounds to obtain the desired convergence rate. The proof involves applying the law of large numbers and the H-diaresis-Older's continuity property of the SDEs, which are essential for establishing the convergence rate. The paper discusses the comparison of two different dynamics, the random batch method, RBM-r, and the interacting particle system, IPS, in the context of large-scale machine learning models. To achieve this, the authors introduce an intermediate dynamics called IPS, which shares the same random batch as RBM-r and IPS. The main approach is to estimate the distance between RBM-r and IPS by comparing RBM-r with IPS, and then IPS with IPS. Firstly, the authors construct a suitable coupling between RBM-r and IPS, using a random time change relation. This preserves the exchangeability of the variables involved, allowing for practical calculations to be made using only the diagonal elements of IPS. The authors then estimate the distance between IPS and IPS, using the random time change relation, the continuity property of the dynamics, and the law of large numbers. This results in an O, square root kappa, upper bound for the distance between IPS and IPS. Next, the authors compare IPS and RBM-r by decomposing the process Z, defined as the difference between the two dynamics, into three parts. The first part is estimated using the strong convexity of the potential function V, the second part is handled through the Lipschitz assumption for the interaction kernel K, and the third part is estimated via the first-order Taylor's expansion and the consistency of the random batch CK. This decomposition leads to an O, 1, square root n, upper bound for the distance between IPS and RBM-r. Finally, combining the results from the previous steps, the authors obtain an O, square root kappa plus 1, square root n, upper bound for the distance between RBM-r and IPS. This indicates that the RBM-r approximates the IPS well when both the time step size kappa and the number of particles n are large enough. The paper also discusses the limitations and assumptions of the analysis, as well as potential future work directions. Here is a combined summary of pages 13 and 14 of the research paper. The authors analyze the dynamics of a system, focusing on the first, second, and third terms of the dynamics equation. They utilize strong convexity, Lipschitz conditions, and the law of large numbers to estimate these terms. Specifically, they demonstrate that the first term can be bounded using strong convexity, while the second term is estimated using the Lipschitz condition and exchangeability of the system. The third term is decomposed into three parts, which are then bounded using the consistency of the random batch and the Lipschitz assumption of the interaction kernel. The authors provide several lemmas that support their proof. Lemma 3.1 establishes uniform in time moment control for the stochastic dynamics, while Lemma 3.2 demonstrates the Holder's continuity property of differential equations. Lemma 3.4 provides upper bounds for the second term on the right-hand side of the dynamics equation, and Lemma 3.5 controls the error brought by the random batch. The authors apply these lemmas to derive an upper bound for the expected squared difference between the interacting particle system and the random batch method. They use Gronwall's inequality to conclude that this difference is bounded by a constant times the square root of the time horizon and the inverse of the number of particles, raised to a power. The authors also provide an upper bound for the Wasserstein distance between the random batch method and the interacting particle system, which is a key result in the paper. This bound is established using the derived upper bound for the expected squared difference and the Gronwall's inequality. Throughout the proof, the authors utilize various mathematical tools, including Ito's calculation, Young's inequality, and the law of large numbers. They also provide detailed proofs for several lemmas in the appendix, which support the main proof. Overall, the authors present a rigorous and technical analysis of the dynamics of the system, providing a comprehensive understanding of the relationship between the interacting particle system and the random batch method. The paper discusses the exchangeability of a system, Z, Ni equals 1, which is defined in RBM-r and IPS. It also provides upper bounds for the second term on the right-hand side of equation 2.13 in step 3 of the main proof. The exchangeability of Z is proven using the Lipschitz condition of K, in assumption 2.1 and an auxiliary result, equation 3.9, which provides detailed calculations on properties of the stopping times such as tau in defined in 2.7. Moreover, the paper presents a law of large number, as shown in lemma 3.3. This result is used during step 2 of the main proof. The detailed calculation is moved to Appendix A.3 for convenience of readers. Additionally, the paper demonstrates a significant finding in equation 3.5, where the authors prove that for fixed t greater than 0, for small kappa, and t is less than or equal to t, we have a specific upper bound for the integral of the expected value of the squared difference between xj, js and xj is over the interval 0, npt. This result is achieved by applying Holder's inequality and combining equations 3.8 and 3.9. The constant c in equation 3.10 is independent of I, j, k, n, p, kappa, t, and t. In conclusion, the paper explores the exchangeability of the system, Z, Ni equals 1, provides upper bounds for the second term on the right-hand side of equation 2.13, and demonstrates a law of large number. These findings are crucial for the main proof and contribute to the understanding of the behavior of the RBM-r and IPS systems. In this research, the authors delve into the analysis of a random batch method, RBM, for optimizing non-convex functions, which is an essential component in various machine learning algorithms. The paper focuses on the stochastic gradient descent method with random batch sampling, aiming to provide a theoretical understanding of its convergence properties. The authors introduce a new framework that combines the stochastic gradient descent method with the random batch sampling technique, providing a unified analysis for both convex and non-convex functions. They also establish an upper bound for the error term, which is a critical component in understanding the convergence rate of RBM. To achieve this, the authors utilize a series of lemmas that control the error brought by the random batch. These lemmas are based on the consistency of the random batch, the Lipschitz and boundedness assumption for K, and the continuity property of differential equations. The lemmas provide upper bounds for the third term on the right-hand side of equation 2.13, which is crucial in the overall analysis. The paper also discusses the time evolution of Xi, I element of Ck, in RBM-r, as given in equation 2.3, for S element of Tk plus 1. By taking the conditional expectation and utilizing the properties of nabla v and k, the authors derive an estimate for E, increment Xi, Fk, as shown in equation 3.17. This estimate is essential in controlling the error term in the analysis. Furthermore, the authors use the uniform moment bound for Xi, as stated in lemma 3.1, and the continuity property of differential equations, as stated in lemma 3.2, to obtain the desired upper bound for the error term. This upper bound is given in equation 3.11, which is a key result in the paper. The paper concludes that the error term in the RBM can be controlled by a function of the batch size and the step size, providing insights into the convergence properties of RBM. This theoretical analysis contributes to a deeper understanding of the stochastic gradient descent method with random batch sampling, shedding light on its applicability and efficiency in optimizing non-convex functions. Here is the combined summary of pages 19 and 20 of the research paper. The authors conclude their paper by summarizing the main results, discussing potential extensions, and providing proofs for lemmas in section 3. Specifically, they prove the convergence of the random batch method with replacement, RBM-r, for interacting particle systems, which is equivalent to the kinetic Monte Carlo, KMC, for pairwise interacting particle systems. The authors demonstrate that RBM-r converges to the associated interacting particle system under Wasserstein 2 distance with an explicit rate, which can be improved when there is no diffusion in the system. The authors suggest that a natural extension of their method is to study the kinetic Monte Carlo applied to other dynamics, such as the stochastic Ising spin system. They propose using their method based on random time change and the law of large numbers to provide a rigorous proof of KMC for suitable models. Another potential direction for future work is to develop advanced analysis tools to improve the current convergence rate from kappa⁻1/4 to kappa⁻1/2, even when the volatility sigma is non-zero. In the appendix, the authors provide detailed proofs for lemmas 3.1, 3.2, 3.3, and equation 3.9. Specifically, they estimate the process xi, t, using Ito's formula and lambda convexity of V, in assumption 2.1. By applying Young's inequality and choosing small nu and nu, they obtain a bound for the second term on the right-hand side of equation, A.1. This leads to a moment control for xi, t, in equation, A.2. The authors also estimate the process xi, t, using the random time change relation and the boundedness of k, from assumption 2.1. They apply Gronwall's inequality to obtain a bound for xi, t, in equation, A.3. Similarly, they estimate the process xi, t, and apply Gronwall's inequality to obtain a bound in equation, A.5. Overall, the authors provide a rigorous analysis of the random batch method with replacement and its application to interacting particle systems, highlighting potential extensions and areas for future work. The authors establish bounds on the expectations of the squared differences between the processes xl, I, xl, x, and z at different time points. Specifically, they utilize Holder's inequality, the polynomial growth of Nabla-V, in assumption 2.1, and the moment control in lemma 3.1 to derive the inequalities. For xl, I, they show that the expectation of the squared difference between xl, I, t2, and xl, I, t1, is bounded by c, t2 t1, 2 plus 3 sigma 2, t2 t1, where c is a positive constant independent of I, L, k, t1, t2, n, p, and sigma. Similarly, for xl, the expectation of the squared difference between xl, t2, and xl, t1, is bounded by c, t2 t1, 2 plus 3 sigma 2, t2 t1, where c is a positive constant independent of L, k, t1, t2, n, p, and sigma. For x, the expectation of the squared difference between xi, t2, and xi, t1, is bounded by c, t2 t1, 2 plus 3 sigma 2, t2 t1, where c is a positive constant independent of I, k, t1, t2, n, p, and sigma. Finally, for z, the expectation of the squared difference between z, t2, and z, t1, is bounded by c, t2 t1, 2, where c is a positive constant independent of I, L, k, t1, t2, n, p, and sigma. In the proof of lemma 3.3, the authors introduce the sequence tau k, which is I, d, and geometrically distributed with expectation e tau ik equals n, p, and variance var tau ik equals n2, p2n page. They then utilize this result to establish an upper bound on the expectation of the squared difference between kate int and npt. In the proof of 3.9, the authors recall the definitions of Nis and tau in, and decompose the integral of the expectation of the squared difference between tau I Nis and tau jnjs into a sum of expectations. They then utilize the results from the proof of lemma 3.3 to establish an upper bound on this integral. Here is the combined summary. The authors derive an upper bound for the integral of the squared difference between two random variables, $tau underscore in underscore is $, and $tau underscore jn underscore js $, where $n underscore is $, and $n underscore js $, are binomially distributed random variables representing the number of times particles with indices $i and $j are chosen into a batch before time grid $t underscore k $. The bound is expressed in terms of the variance of $n underscore is $ and $n underscore JS$, which are shown to be $k plus 1 p underscore n, 1 p underscore n, $, where $p underscore n$ is a parameter. The authors use the Tower property and the mean and variance of tau underscore in underscore is $ and tau underscore jn underscore JS$ to rewrite the integral as a sum of three terms. The first two terms are bounded using the mean and variance of $n underscore is $ and $n underscore JS$, while the third term is bounded using the variance of $n underscore is $, and $n underscore JS$. The final bound is expressed in terms of the parameters $and $p underscore n$ and $kappa$. The authors also provide a list of references, which includes papers on binary interaction algorithms, characterization of radially symmetric finite-time blowup, scaling theory for metastable states, plasma physics via computer simulation, and kinetic limits for pair interaction-driven master equations, among others. In summary, the authors derive an upper bound for the integral of the squared difference between two random variables, which is expressed in terms of the variance of the random variables. The bound is used to analyze the behavior of particle-based models of swarming with uncertainty. This paper presents a comprehensive overview of the random batch method, RBM, and its applications in various fields, including interacting particle systems, quantum Monte Carlo simulations, and molecular dynamics. The RBM is a stochastic approximation method that has been used to estimate the mean field limit for large interacting particle systems with Coulomb interactions. The method has been shown to be efficient and scalable, making it suitable for complex systems where traditional methods are computationally expensive or intractable. The authors discuss the convergence properties of the RBM, including error estimates and propagation of chaos. They also provide a detailed analysis of the RBM for second-order interacting particle systems, highlighting its near-optimal rates without convexity. Additionally, the paper covers the application of the RBM in quantum Monte Carlo simulations, demonstrating its ability to solve integral equations of classical potential theory rapidly. The paper also touches upon the use of the RBM in molecular dynamics, particularly in the context of the Ewald method. The authors discuss improvements to the Ewald method using the RBM, leading to superscalability in simulations. Furthermore, they address the limitations and assumptions of the RBM, pointing out areas for future work. The paper concludes by summarizing the key findings and highlighting the potential of the RBM as a versatile tool for solving complex problems in various fields. The authors emphasize the importance of further research to fully exploit the capabilities of the RBM and to explore its applications in other domains.